this movie, we want to focus on the potential difference across various parts of a circuit which is broken. So previously, I asked you to predict each of these values, V1 up till V8, and then we solved for some of them because we saw that the potential difference across a good conductor is always 0 volt, but we still have to solve for these. Now, V6 is actually very easy because this circuit is a complete circuit, and the battery is putting in 9 volt. The bulb is the only resistor in the circuit, so it must take all of those 9 volts out. So V6 will be 9 volt. In this movie, we want to focus on this kind of circuit, a broken circuit, where there's a switch that's open. And how does that affect the voltage across the open switch and the voltage across other components in the circuit? So make sure that you have predicted V3 and V2's values before we continue. Now remember, in a circuit, the battery puts voltage in. In other words, it puts energy, joules of energy, into the charges. And the resistors take voltage out. In other words, they convert electrical energy into other forms of energy, heat energy, if it's a bulb or an LED, also light energy, and those kind of energies go out of the circuit into the surroundings. And the amount of energy that the battery puts in is equal to the amount of energy that the circuit's resistors take out. And how the circuit's resistors remove that voltage or share that voltage between them is determined by the ratio of the resistance. So in this particular circuit, 1K is half of 2K, or we can say 2K is double 1K. The ratio of the resistance is 1:2. And that's why the ratio of the potential difference across the two resistors is a potential difference of 3 volts, and that's a potential difference of 6 volts. That is also 1:2. 3:6 is a ratio of 1:2. So the ratio of the resistance determines the ratio of the voltage across, or the potential difference across the resistors. Now let's work with that a bit to help us to understand open circuits. Here we have a circuit where there's a certain potential difference across a battery. We can take it to be 9 volt if you like, it doesn't really matter. Whatever potential difference across a battery. And we have two resistors in a circuit, R1 and R2. Now R2's value is constant, but R1 is a variable resistor. It's quite an amazing variable resistor because its resistance can be changed from 0 ohm all the way to infinity. In other words, like an open switch, like an insulator. So we are going to look at 5 setups of this circuit. So each of these 5 stands for one orientation of the variable resistor. First of all, the variable resistor is going to have 0 ohms. Notice resistor 2's value is constant, as shown by the R2 sizes being the same for all situations. Then we're going to increase the variable resistor, but it's going to be quite small, less than the resistance of R2. Then we're going to increase the variable resistor's resistance to be equal to R2, and then it's going to be even greater than R2. And then we continue the trend. You see how we have a trend from 0, greater, until the maximum of that trend, where we have resistor 1 being an open switch, infinite ohm resistance. And all this time, resistor 2's value remains constant. And the issue is, how is the potential difference across the two resistors going to change in these 5 situations? Now we know that there is only a certain amount of voltage that the battery gives. Let's say 9 volt. So the sum of the potential differences across the two resistors has to equal, if this is 9 volt, that same 9 volt in every case. Whatever value the battery puts in, the resistors together have to take out. But how that 9 volt is shared between the two resistors will not be the same between the 5 situations. How will it differ? Pause the movie while you predict this. When resistor 2 is connected to a good conductor, in other words, 0 ohm resistance, then resistor 2 is the only resistor in the circuit. It will take the full supplied voltage, let's say 9 volt. If resistor 2 has a greater resistance relative to resistor 1, resistor 2 is greedier in comparison to resistor 1, so it will take more more of the voltage than resistor 1 takes. Put another way, the ratio between resistor 1 and resistor 2 lies more heavily on the side of resistor 2, so it will take a greater proportion of the supplied voltage. Now we have resistor 2 and resistor 1 both having the same resistance. So the ratio of the resistance is 1:1. Therefore, the ratio of the voltage across them will also be 1:1. They will share the voltage equally in this situation. If it's 9 volt that the battery supplies, each will get 4,5 volts. If resistor 1's resistance is increased to become greater than that of resistor 2, now the ratio between them lies more heavily on the side of resistor 1, so it will take a greater proportion of the voltage, leaving less for poor little resistor 2. And if we continue that reasoning to its extreme, if resistor 1's resistance is infinite ohms, then the ratio between the two lies so heavily on the side of resistor 1 that it only lies on a resistor 1 side. Resistor 1 is so greedy that in comparison, it's as if resistor 2 is a good conductor. And so the open switch of infinite resistance would take all the voltage. If the battery supplies 9 volt, 9 volts will be across that open switch. So take a look now again at that circuit which you needed to predict about. Do you agree with the prediction you made earlier? Maybe you want to make a change. Can you see that this 9 volts has to be shared between these two resistors? This is how we could view it. Where this resistance has infinite resistance. In comparison to infinite resistance, this one is as if it's a good conductor, as if it has 0 ohms. So S1 takes all the supplied volts, the full 9 volts, leaving nothing at all for V2. Now there's one thing about this which I've explained which you might not be so very happy about, and that is, how can this resistor take 9 volts when no current anyway flows through the circuit? It's true, no current flows through a broken circuit. But this way of thinking is still useful because it gives us the right answer. But let me give you another way to think about it too, which might make you more happy if you don't like the explanation I gave before. Let's look at it from the perspective of measuring EMF. We know that EMF is the voltage across a cell or battery when no current flows through that cell or battery. This is a very clear way to measure EMF. Simply place your voltmeter straight across the cell or the battery. There's no external circuit, so there's no current flowing through the battery, and we simply measure the voltage across it. But can you see that this is actually also a way of measuring EMF? Because here again we have a voltmeter, and one side of the voltmeter is connected to the negative terminal of the battery, and the other side is connected in effect also by good conductors to the positive terminal. Why? Because remember, in comparison to an open switch which has infinite resistance, any resistor is as if it's a good conductor. So in this setup, it's effectively the same as the previous setup. One side of the voltmeter is connected by a good conductor to the negative terminal, and the other side of the voltmeter in effect is connected by good conductors to the positive terminal. So when we are measuring the potential difference across S1, when S1 is open here, we are actually measuring the EMF of the battery. So if the battery has an EMF of 9 volt, then that reading there would be 9 volt. If the battery had an EMF of 1,5, then it would be 1,5 volt. Whatever the EMF of the battery is, that voltmeter will read it. Now there's yet another way we can look at this, which might also be useful. Remember that voltage, which is energy per charge, can be either potential or potential difference. And it's important not to confuse these. Potential refers to how much energy each charge has, whereas potential difference refers to the change, whether it's a gain or a loss of energy per charge between 2 points. We've already discussed that all points joined by a good conductor are at the same potential. These points are joined by a good conductor. They are all at the same potential, which happens to be 9 volt. The potential in this wire is 9 volt at every point. These points all at the same potential, which happens to be 3 volts everywhere. And these all at the same potential, 0 volt everywhere. Remember Remember, that's not the same thing as potential difference. If we took the potential difference across there, there's no change in potential. 9 minus 9 is 0 volt. 0 volt potential difference. Between there and there, 0 volt potential difference. 3 volt minus 3 volt is still 0 volt difference. And there it's easier to see. So now let's use this reasoning to help us to understand the potential difference in a broken circuit. So let's look at this circuit again. Remember that an open switch has infinite resistance. In comparison to that, any resistor is as if it's a good conductor with 0 ohm resistance. All points joined by a good conductor are at the same potential. Let's say that this is a 9 volt battery. All these points here are joined by a good conductor. Remember, the bulb in this situation is as if it's a good conductor in comparison to the open switch. So every point is at a potential 9 volt. These are potentials, not potential differences. And then here, all of these points are joined by a good conductor to the negative terminal of the battery, and the negative terminal is at 0 volt potential. So all of these points are at 0 volt. And so this voltmeter here is measuring 0 volt on one side, 9 volts at the other side. It gives us the difference 9 minus 0 volts, which is 9 volt potential difference. So let's apply this reasoning to the circuits which we're using for prediction. Let's start off with the complete circuit. These points are all joined by a good conductor, so they are all at the same potential. That potential is 9 volt because it's connected to the positive terminal, and we are told that the battery has a potential difference of 9 volt, which means the potential at its positive terminal is 9 volt. These points here are all joined by good conductors to the negative terminal, so they are all at 0 volts. This voltmeter gets the difference. It feels 9 volt there, it feels 0 volt there. It tells us the difference 9 minus 0 is equal to 9 volt. That is the potential difference across the bulb. V6 is 9 volt. Now let's turn to the broken circuit. In comparison to an open switch, this bulb is as if it is a good conductor. So all points connected here, including the bulb, because in comparison to the open switch it's like a good conductor, are at the same potential. That potential is 9 volt because it's connected to the positive terminal, and we're told that this is a 9 volt battery. There's the negative terminal. All points there are connected to the negative terminal and are at the same potential, 0 volt. So now, what will each of the voltmeters read? Start off with voltage 2. Voltmeter 2 feels 9 volt on this side, 9 volts on that side. It gives us the difference between the two, 9 minus 9, which is 0 volt. Voltmeter 3 feels 0 volts on one side, 9 volts on the other side. Gives us the difference 9 minus 0 is equal to 9 volt.